Okay, good morning.
Good morning.
Today, let me gotta turn my volume up. I didn't even have my volume on. I couldn't even hear you guys. Okay. Um, any questions? Any questions from chapter 6, which was really from last week, but this week I guess you guys will be doing the exam. So if you have any questions, this is a good time to ask. Okay. All right. So what I want to do today is I want to start talking about chemical bonding. We're getting close to the end here. And it leads into sort of our final topic, which is chemical bonding. And so now we've done all the quantum chemistry, the quantum mechanics about the structure of the electrons around the atom. And we've talked about gases and moles and all that stuff. Now we're going to talk about chemical bonding. And so we're going to focus on covalent bonding, but I do want to make one little mention about the two different types of bonding. Generally, we break it into two categories. We have what's called ionic bonding. By the way, this is chapter 8. And ionic bonding is what happens when you have charged atoms that are near each other. The opposite charges are attracted to each other. So what they do is they form complexes. They essentially attach to each other. And so what will happen is you'll get arrangements that look something like this. You'll have a bunch of these ions, and they will locate themselves nearest the opposite charge. Okay, so really what you end up with is a really large cluster. You don't end up with like 2 atoms or 3 atoms or 4. You end up with a huge number. So like each grain of salt is actually, 10 to the 18th or 10 to the 19th of these ions all clustered together into one large particle that you can actually see with your eye. So the attraction is really between these ions. They're opposite, right? Remember, opposites attract. So if you have a positive ion and a negative ion, they'll attract to each other. So that's really what ionic bonding is. So you see this in things like sodium chloride and calcium oxide, for example. So the key here is that if you have a metal and you have a non-metal, that's typically when you see ionic bonding, when you have a metal and a non-metal. Okay, now it's more complicated than that. There are compounds that have metals and non-metals, and they actually have what we would call covalent bonding or other types of bonding. But in general, if you have a metal with a non-metal, they will combine in this way. Of course, the metal is the one that's positive. Metals tend to lose electrons, and then the non-metal is the one that's negative. Okay, so positive, negative, positive, negative. And I'm not going to say much more about ionic bonding here because the main focus on this chapter is with covalent bonding. So let's move on to that. In a sense, it's a little more interesting. Covalent bonding is the case where atoms share electrons. Okay, and when atoms share electrons, these shared electrons are called covalent bonds. So covalent bonds are the case where you have shared electrons, and you tend to see this between nonmetals. That's where it's mainly observed. And again, it does happen with metals as well, but to a much less extent. It's more focused on the nonmetals. So let's talk about the elements where you see this covalent bonding. The first is hydrogen. Element number 1, hydrogen is very commonly involved in covalent bonds. Now, The other elements where you tend to see this are boron, carbon, nitrogen, oxygen, and fluorine. So I'm sort of drawing a little partial part of the periodic table here, right? So the second row, this is your second row of the periodic table. It's most of those elements on the right side. And then below that, silicon, phosphorus, sulfur, chlorine. This is your third row of the periodic table. Below that, it's arsenic, selenium, and bromine. This is your fourth row. And then I'm going to put iodine here. Now, I'm not being this is not an exhaustive list. There are other elements that possess covalent bonding phenomena. But these are the main elements where you see covalent bonding. And really what's useful for this is that since we are biological organisms that have large amounts of these elements right here, right? So these are biological elements, including this one over here. This has significant applications for biology because many of the macromolecules that are observed in biology, whether it be ATP or DNA or proteins or carbohydrates or lipids, they primarily involve those 6 elements that I've circled right there. And so covalent bonding, much of the efforts over the years to develop theories of covalent bonding are driven by that need to develop drugs, medications, and an understanding of how biology works, how it functions. Okay, so let's talk about the covalent bonding. Essentially what happens is you have an atom. So let's take, for example, a hydrogen atom. The hydrogen atom only has one electron, and what I'm going to do is I'm going to represent that electron with a dot. Okay, that little dot, we call it a dot. It represents the electron in that hydrogen atom. And notice that hydrogen has one electron. So the symbol that I'm using here, I have a symbol for the element, which is the H. That is meant to represent essentially the nucleus of the hydrogen. So the H means the nucleus, right? And then the dot refers to the electron. And what we're doing is we're drawing the dot away from the nucleus, away from the symbol, so that we can talk about how it's going to interact with other atoms. That's really what we're talking about, how atoms interact with each other. And so I'm going to take another hydrogen atom, a second one, and draw it right next to it. And I'm going to write its electron on the opposite side so that it's facing the first hydrogen, and that's a dot. So each hydrogen has one electron. And what's observed is that as those two atoms come closer to each other, the two electrons will interact with each other. But remember, electrons are negatively charged, right? So they're not attracted to each other. They're repelled by each other because of that negative charge. But quantum mechanically, they can exist in the same orbital. So what can happen is those two electrons can move into an orbital, spin up and spin down. And so those two electrons are in the same orbital. Now, why would they do that? They're negatively charged, so they shouldn't want to be anywhere near each other. Well, the answer is, by doing this, each electron is now attracted to each nucleus. So both electrons exhibit an attraction for that nucleus, because remember, the nucleus is positively charged. So now these negatively charged electrons are attracted to it. Likewise, they can also be attracted to this nucleus here. There's attraction occurring there. So by occupying the same orbital, one spin up and spin, one spin down, they now are they're able to interact with both nuclei. Look at it this way. You've got positive nucleus for this hydrogen, You've got a positive nucleus for this hydrogen, right? These are positive charges. Now these two electrons, what they'll do is they'll essentially occupy an orbital so that they can interact with both of those nuclei. Remember, both electrons are negatively charged, so now those two negative charges are attracted to both nuclei. Also keep in mind that they are waves. They're not, in some sense they're particles, but in another sense they're waves. So that both of those electrons are spreading their waves out, their wave functions we call it, across both nuclei. So they're interacting with both. And so now this becomes one large particle. It's got two nuclei and two electrons. And the whole thing is a cluster of four particles. Both electrons are attracted to both nuclei, and both nuclei are attracted to both electrons. And so we call this pair of electrons, we call this a covalent bond. And that covalent bond is the case where you have a pair of electrons attracted to both nuclei, holding the nuclei like a glue. So it'd be kind of like two magnets that are attracted to each other. You have two magnets, they're pulling on each other. That's what the electrons are doing. They're essentially pulling those nuclei together, even though the nuclei want to be apart because they're both positively charged, so they're both repelling each other. So we call that a covalent bond. These are called dots. And what I'm going to do is I'm going to show you how you draw out the dots for all of these elements over here on the nonmetal side. Okay, it's very simple. So these are called electron dot structures. And typically we do it for hydrogen, but you can also do it for some of the metals, not all of them, but a few. So you can do it for this first column, the alkali metals and hydrogen. Again, hydrogen is a nonmetal, typically considered a nonmetal, but these ones are metals below it. You can also do it for the second column, but typically it's not that useful. It's really these Lewis dot symbols or Lewis dot structures. These are really useful for the nonmetals. So you get, for example, boron, carbon, nitrogen, oxygen, fluorine. And you can even do it for the noble gases, but again, it's not all that helpful. You can do it for aluminum, and you can do it for silicon and phosphorus and sulfur and chlorine and bromine. So I'm just going to put some of them down here, but I'm going to give you the lowdown on how to do this. The way it works is the electrons that are involved in bonding, so we'll call them bonding electrons, are typically the outermost electrons in an atom. The outermost, and those are called valence electrons. Valence are the outermost electrons. So let me give you an example. If you look at carbon, for example, carbon is 1s2, 2s2, 2p2. That's the electron configuration that we learned back in chapter 6. The outermost electrons, when I say outermost, I mean the ones with the highest N value, the highest principal quantum number. So for carbon, the highest N is 2, right? The principal quantum number is 2 there. So those would be the outermost electrons. Those would be the valence electrons. So what you do is you count them. How many electrons are there with N equals 2 for carbon? Well, remember the superscript is the number that tells you how many electrons there are in the subshell. So there's a 2 and there's another 2. So you have 4 valence electrons. You just count up the superscript, and that will tell you how many valence electrons you have. And then what you do is you draw the symbol, and you take that number 4 and you represent it as dots. And it's useful to think of the symbol kind of like a square. I'll draw a little dashed line to kind of show you what I mean. Think of that as a square. You got 4 sides on a square. So if you have 4 electrons, put 1 dot on each side of the square. So you can have up to 2 electrons on each side. So that's essentially what we would call the Lewis dot symbol. And let's try another one. Let's try, for example, chlorine. So chlorine has 17 electrons. So its electron configuration is this. Okay, I just did it very quickly. The highest value of N is 3, so that would be the valence electrons. There you go. So you count up the superscripts. 7, right? So you got 7 valence electrons. So then you write the symbol, and then you got to put 7. So, you know, just count around. 1, 2, 3, 4. We've gone around all 4 sides. 5, 6, 7. So now you got 7 dots. So this would be the Lewis dot symbol for chlorine. Now, what happens is that gets kind of tedious if you have to go doing the whole electron configuration and then figuring out what you're going to have there. So here's what happens. There's a pattern to the periodic table. And the pattern is you can tell how many valence electrons there are just by looking at the column. And here it comes down to this. So if you're in the first column, there's 1 valence electron. If you're in the second column, there's 2. If you're in this column over here, 3A we call it, there's 3, then 4. You can even include arsenic here. 5. You can even include selenium here. 6. See, the numbers are consistent with what I just did for carbon and for chlorine. Carbon, I said it was 4, and there you go, there's 4. And then chlorine, I said it was 7. There you go, it's 7. So remember, the valence electrons is not necessarily all the electrons. It's just the ones with the highest value of N. But for Lewis dot symbols, it doesn't matter whether N is 1 or 2 or 3. We just need to know the number of valence electrons, so we can use their position in the periodic table to figure out how many that is. So if I were now to say, let's do aluminum. Here's aluminum. How many valence electrons does it have? 3. We know it right there. So we don't even have to go through the 1s2, 2s2, 2p6 and all that. We just look it up where it is in the table. So 3. So then we write Al, 3 dots, 1, 2, 3, and there's your Lewis dot symbol for aluminum. Very, very simple way to do it. Doesn't require us to do much analysis, okay? So notice the pattern. It increases, the number of valence electrons increases from the left to the right till you reach a maximum of 8, right? Notice that number there, 8. Once you get to these elements over here on the right, you're maxed out. Essentially comes up to 8, okay? Notice transition metals, not in here. It turns out that this type of analysis doesn't work very well for transition metals, so we just ignore it. We're just going to deal with these elements that are listed here. Okay? So now, oops, save that one. Now what we can do is we can talk about drawing Lewis structures. And Lewis structures are based on the idea that electrons form pairs attracted to both nuclei. Oops, I misspelled that, nuclei. Remember, the nucleus is the center of the atom. That's where the protons are, and the protons are positively charged, right? Electrons are negative, protons are positive. They're attracted to each other. So here's how we go about it. What you do is you say, okay, here's your hydrogen. Let's do carbon. So those are our Lewis dot symbols. what will happen is each atom will provide one electron to form a pair. So there's your covalent bond. Okay, those two nuclei are now attracted to each other. And then what happens is we generally draw it this way. Whenever you have a pair of electrons that are shared, you draw it as a line. Okay, so this is what we're going to use. This is called line notation. This is the most common way to represent covalent bonds. And since it's one pair of electrons, remember a pair is two, we call that a single bond. A single bond. Single bond typically means a covalent bond. If it were an ionic bond, we wouldn't call it a single bond. But a covalent bond, the sharing of two electrons by two atoms, is called a single bond. Okay? So what happens is, suppose you have 4 hydrogens. What will happen is they will surround the carbon atom based on where the electrons are around the carbon atom. So the carbon atom has 4 electrons, 4 valence electrons. Each hydrogen has 1. So what the hydrogens will do is their electrons and their nuclei will move around the carbon until they can find those electrons. And then you'll get covalent bonds formed. And here's something that's kind of interesting about this. So there's your 4 bonds. Again, the notation we would show is a line. This is called line notation. This is the most common way to represent a bond, a covalent bond. What happens is energy is released. It's an exothermic process. So when bonds are formed, energy is released. And that's a very powerful aspect of chemical reactions, is that when a bond is formed, when you make a new molecule, right? This is a new molecule. We had atoms. These are atoms. So you got 5 atoms. These are separate atoms. Now we have a molecule. When that happens, when you make a molecule, energy gets released. It's an exothermic process. So there's a tendency in nature to favor the formation of molecules over atoms. So it's not surprising that we have planets, because what happens is all these atoms that are bouncing around in the universe, when they get close to each other, they have a tendency to form these covalent bonds. And when they form these covalent bonds, energy is released, and that is a favored process. So now you have these rocky planets and you have these molecules in space. In fact, spectroscopy can be used. We can actually, measure the light coming off of different particles in the universe. And it turns out all over the universe, there's all these molecules floating around in space. Some of the molecules that we see here on Earth. In fact, some of the molecules that we believe were the first molecules to actually form bonds and form the molecules that are seen in life now. They're precursors to life molecules out in space, because the formation of these covalent bonds is a favored process in terms of energy. Energy favors it, so it's exothermic. Okay, so this is a molecule. This is referred to as a Lewis structure. When you draw the line notation for a molecule, we call that a Lewis structure, named after G.N. Lewis, who was the first chemist to kind of develop this idea of showing molecules using these structures. It's a convenient way to think about things. Okay, so mainly what you're going to do, you'll do some other things in this chapter, but mainly what you'll do is you'll just practice drawing Lewis structures and analyzing Lewis structures and figuring out which ones will form and which ones will not. So what happens is we have this phenomenon, which is called the Octet Rule. And the Octet Rule is a very powerful rule. What it says is that atoms again, typically we're talking about nonmetals, tend to form covalent bonds with other atoms such that each atom has 8 octet valence electrons that are shared with the other atoms. Wait, let me write another atom. Or contained solely by the atom. Solely, meaning only by itself. So you see the octet rule in this molecule here, methane. This is CH4. If you count up all the electrons, all the valence electrons around the carbon, okay, each line, remember, each line is 2 electrons, so that's 2. There's another 2. There's another 2. There's another 2. You get 8. That's 8 electrons, and that's the octet rule at work. 8 electrons around that carbon atom. Now notice hydrogen doesn't have 8. So hydrogen is an exception to that. Hydrogen does not obey the octet rule. Hydrogen has its own rule. 2 electrons. And we call that the Duet Rule. Okay. So each hydrogen only has 2, right? So the idea is any electrons that are either shared by 2 atoms or only on that one atom, that atom counts all of those electrons. So the carbon now has 8 electrons. Remember, it started with 4, right? The Lewis symbol for carbon was 4. But now when you're in CH4, now the carbon has 8. And that's the octet rule. So covalent bonding is driven by this phenomenon, this very simple phenomenon that atoms will try to have 8 valence electrons. Now, why 8? Why not 9? Why not 10? Why not 13? Well, it really comes down to noble gases, interestingly enough. What happens is, if you look at the noble gases, they give us a little hint. The noble gases, they all have 8 valence electrons. Neon, argon, krypton, and xenon. And so that's really what's going on. There's something significant about 8 that gives these elements a stability. And we can explain it through, you really can't explain it unless you use quantum mechanics. It's really the only theory that can explain why the octet rule exists. And here's our explanation. If you remember the box notation, the box diagrams we talked about last week for the S and the P, so the S has 1 orbital, so that's a maximum of 2 electrons. And then the P has 3 orbitals, so that's a maximum of 6 electrons. Look what happens when you add those up. You have 2 electrons plus 6. That gives you 8 electrons. So the reason this octet rule seems to be observed in nature is by having 8 valence electrons, you're filling out this entire shell. So the shell is now filled. And that seems to provide stability. Okay. So that's the noble gases, right? So the noble gases, neon, argon, krypton, and xenon, they've all, they got 8 valence electrons there, right? So what happens is when carbon starts off with 4, well, that's only 4, that's not 8. So it's got room for 4 more electrons. So what happens is each hydrogen provides 1. And so that provides an extra electron for each one. So now the carbon has 8. and there's your octet. And essentially what happens is carbon now has the same number of valence electrons as neon, which is in the same row, okay? So very powerful. Now we shouldn't overestimate the octet rule. The octet rule works for certain elements, but not all the time. But it's pretty good with carbon, nitrogen, oxygen, and fluorine. It's very rare to see any examples where those elements don't have 8 electrons in a Lewis structure. It can happen, but it's very rare. So it works really well with those elements, but there are exceptions that we want to study. So let's draw a couple Lewis structures. Let's start off with a couple of simple molecules, water and ammonia. Okay, very simple. Here's what you do. The first step is you look at the formula, H2O. You locate the element where there's only one atom, right? So in water, there's only one oxygen. And you put that at the center. So whichever element, there's only one atom, you put it at the center. Then you look at the other element and you surround the central atom with those. So these go, there's 2 of them, right? So you put 1 on either side. Those are called surrounding atoms. So the one where there's only one atom, you put at the center, that's called the central atom. The one where there's more than one, you put them on the surrounding. So those are called surrounding atoms. Then you count valence electrons. So, you go back to your periodic table. If you count them up, what you'll find is hydrogen has 1 and oxygen has 6. Okay, so what you do is you say, okay, how many is that? Each hydrogen has 1. And the oxygen has 6. So that's a total of 8. So we got 8 electrons. Okay, so you got 8 valence electrons. You then assume that the central atom has 1 bond to each surrounding atom. Okay, so count your valence electrons. In this case, we have 8. Then assume 1 bond between the central atom and the surrounding atom, each surrounding atom. Surrounding atoms do not tend to bond to each other. So it's just the central to the surrounding. Now, each time you draw a bond is 2 electrons. Remember, it's a pair of shared electrons. So that's a total of 4, because you got 2 here and 2 here. So that's 4 electrons. So you subtract. You started with 8. Now we're going to take off 4. So now we're down to 4 electrons. Then you apply the Duet rule for hydrogen. Hydrogen can have 2, and the Octet rule for the other element, for the central atom. So oxygen is the central atom. It can have 8 octet. So what you do is you say, okay, how many should hydrogen have? Well, hydrogen already has 2. It's got 2. It's got a bond. This hydrogen already has 2. It's done. We already got the duet. So don't add any electrons to hydrogen. But the oxygen needs 8. So what we do is we write 2 pairs on opposite side. You put them on opposite sides. So you see you got 4 there. I'm going to write them as individual pairs around the oxygen. And that's called it has 2 names. Most typically we call it a lone pair, meaning it's a pair of electrons only on one atom. It's also called a non-bonding pair, because that's a pair of electrons it's not involved in bonding, right? It's only on the oxygen. This is a bonding pair because both electrons are between the 2 atoms. They're holding the atoms together. So now think of it kind of like balls with springs. You've got 3 atoms, 2 on the outside, 1 in the middle. They're attached to each other by these electrons, but the electrons are not physical objects. They're really just forces. They're really just energies. So what happens is the atoms are going to vibrate like springs. And so you've got 3 atoms attached together. The total number of valence electrons is 8. The oxygen has 8. Each hydrogen has 2, and that's your Lewis structure for the water molecule. We don't have to show any shapes here. Chapter 9 deals with shapes. Typically, even though the water molecule is bent, the Lewis structure is just a straight line. We don't need to put the arrangements any more detailed than it's shown there, okay? So if the question was, how many lone pairs does the oxygen have? The answer would be 2. There's a lone pair on the top and there's a lone pair on the bottom. How many bonding pairs are there? Well, there's 2. There's 1 to each hydrogen, so that's 2. How many valence electrons are there? There's 8. Which element is obeying the octet rule? Oxygen. Which element is obeying the duet rule? Hydrogen. Hydrogen is the only element in Lewis structures that obeys the duet rule. Okay, let's try the ammonia, Nh3. So again, what you do is you look at the formula. One of the elements, there's only one atom, and that's the nitrogen. So that goes at the center. Then you locate the surrounding atoms. There's 3 of them, so you put them on the outside. It doesn't matter whether you put them on the top or the bottom or the side. Just, again, think of like a square, and you're putting them around sides, but it doesn't matter which sides you pick. So there we go, Nh3. Then we count the valence electrons. And remember, what I'm doing is I'm going back to the periodic table. Oops, I forgot oxygen. You're looking at where they are. So nitrogen is in column 5, so that means it has 5 valence electrons. Hydrogen is in column 1, so it has 1 valence electron. So each hydrogen has 1 valence electron. Nitrogen has 5. So that's a total of 8 electrons. So then you assume 1 bond between the central atom and each surrounding atom. 1 bond. Remember, a bond is 2 electrons. So we've now used 6 electrons, right? If you have 3 bonds, there's 2 electrons per bond. So 3 bonds times 2 electrons per bond. That's going to give you 6 electrons. Then you say, okay, we've used 6. We still got 2 left because we had 8. So you got 2 left. Where do you put the 2? You put them on the central atom to get it up to the octet rule. Remember, octet. So hydrogen duet, the other element's octet. So you take that 2 and you write them as a pair. And that, again, is a lone pair. So this is ammonia. Ammonia is a very important molecule. This is water, of course. Water, of course, is also a very important molecule. They're both kind of similar in a way. They both have lone pair on the central atom. Water has 2, ammonia has 1. They both have hydrogens surrounding the central atom. There's other similarities as well, but this would be the Lewis structure for ammonia. Okay, so we've done 3. We've done 4. We did hydrogen. Actually, we didn't do hydrogen. I'm sorry, we've done 3. So we did methane, CH4. We did water, H2O. And we did ammonia, NH3. They're all kind of very similar. Hydrogens as the surrounding atoms. CH4 didn't have any lone pairs. Water has, right, CH4, that's actually over here. No lone pairs on the carbon, right? Just bonding pairs. Single bonds, bonding pairs, no lone pairs. Water had 2 lone pairs, and then ammonia had 1. Okay. You can also apply this to some ions, as long as they're ions that don't have metals. So in terms of ions, it's kind of interesting. So I'm going to show you a few. Let's do the hydroxide ion. Right? Hydroxide is important for bases, right? And then there was an important ion for acids. This was our hydronium ion. Let's see, can I do any others? Most of the ions have double bonds or triple bonds, so I'll just do these 2 for right now. Actually, no, there's one more. We can do ammonium. We'll get to double and triple bonds in a little bit. So there's 3 ions. You can also use them. Remember, there's no metals here, right? So you can also use Lewis structures. Here's the trick. If you have a negative charge, that means it has an extra electron. Negative means 1 more electron. So you add 1 electron to the total. Okay. If you have a positive charge, that means it's lost an electron, right? It's actually oxidation when you lose an electron. So you lose or subtract. Let's use the mathematical term. You subtract 1 electron from the total. And then there's a positive, so you subtract 1 electron. Now, why 1, not 2? Because it's plus 1, right? If it were plus 2, you would actually subtract 2 electrons. And if it were minus 2, you would add 2 electrons. So you add the number of electrons or subtract based on what the actual amount of the charge is. You don't generally see ions with a charge of plus 4 or plus 5. But if you did, you would subtract 4 or 5 electrons. You generally don't see minus 4 or minus 5. But if you did, you would add 4 electrons or 5 electrons. Okay. So let's check these out. Remember the valence electrons, hydrogen is 1, and then nitrogen was 5, and oxygen was 6. Fluorine was 7, neon was 8. Okay, so for this one, we're just going to use 3 elements. Hydrogen, which has 1. Nitrogen, we're going to do that, it has 5, and then 2 of them have oxygen, which is 6. So let's go through it. So oxygen, 6 electrons, hydrogen 1, but you have this negative, so you're going to add 1 more. So it's 8 electrons. Notice how all of these have 8 electrons. A lot of them have 8 because of the octet rule. It's very common in nature. 8 electrons. There's other multiples that are important, that are common as well. 16, 24, even 32, because those are multiples of 8. So there's certain patterns that we've figured out about the structures of molecules in nature and ions. So let's do H3O plus. So you got 1 for each hydrogen. So I'm going to write it this way, 3 times 1, right? Because if you got 3 hydrogens and each one's 1, that's 3. Then you got an oxygen, but it's positive, right? So that means you subtract 1 from the total. So what you get is 11 minus, oh, I'm sorry, oxygen's not 8. Oxygen is 6, right? Why did I put 8 for oxygen? I don't know. 6 for oxygen. So 3 plus 6 minus 1 is 8 again. So again, you got 8 electrons. Let's do the ammonium. Ammonium has, nitrogen has 5. Each hydrogen has 1, but then you have a positive, so you subtract 1. So that's 9 minus 1, again, 8 electrons. So 8 is very common. It's relatively rare to have these really little molecules, these simple molecules with 9 electrons or 7. They typically have 8. There are some, there's this molecule called nitrogen monoxide, which has 9, but it makes it very unusual molecule. Okay, so let's now do the Lewis structure. So here we don't have to worry about the central atom because there's only 2 atoms. You can't have a center if you've got 2. You need to have at least 3 atoms to have a center. So all we got to do is just write them next to each other, OH. And then assume 1 bond. We'll look at structures later that have more than 1 bond between the atoms. Those are called double and triple. But for now, we're just looking at the simple ones. Okay. So then you count up your electrons. You got 8, but we've already used 2, right? Each time you write a bond, that's 2. So 8 minus 6. I'm sorry, 8 minus 2 is 6. So then you do duet for hydrogen and octet for the other elements. So hydrogen already has 2. It already has duet. So you got 6 electrons. So you write them as pairs around the oxygen. And it works out perfectly. By drawing those 6 electrons, now the oxygen has 8. Now, if it's an ion, what we're going to do is we're going to draw a little bracket around each side and then put the charge outside the bracket. Okay, that bracket notation is used for ions. Okay, that's just to indicate that the charge of this Lewis structure is minus. The hydroxide is minus. Okay, let's do the hydronium, H3O+. Now we do have a central atom, right? Because you got 3 hydrogens, so that means the oxygen's at the center. And again, you assume there's one bond between each surrounding atom and the central atom. There's got to be at least one bond, or it wouldn't be a molecule, it wouldn't be a Lewis structure. So there's 6. So, but we got to have 8. So I've already used 6. So 8 minus 6, we got 2 left. We could put them on the hydrogen, except that hydrogen obeys the Duet Rule. I've never seen an actual structure where hydrogen has more than 2 electrons. In theory, it's possible, but it's very rare and it's not stable. So just use the duet for hydrogen. So we got 2 electrons left, put them on the oxygen, and now the oxygen has 8. 2, 4, 6, 8. Again, you got to do the brackets and then put the positive outside the bracket. Now, sometimes I've seen it done this way. Instead of doing a double bracket, they just do one-sided bracket. So I've seen that too. So if you see that out there, don't worry about it. That's essentially saying the same thing. Sometimes people use a double bracket. Sometimes people use a single bracket. But the single bracket is essentially telling us the same thing, that this whole thing is +1. And now we can do the ammonium. The difference here is that nitrogen has 5 valence electrons, whereas oxygen had 6. So you got 5 plus 4 times 1 minus 1. So you got 8. Again, it's 8. Nitrogen at the center. Assume one bond to each hydrogen. Okay, now you count up your electrons. Each bond is 2, 2, 4. We're out of electrons. We've already used 8. So there's no lone pairs here. But again, don't forget the brackets. It's an ion, so it's got to have the brackets and then the charge outside that. Okay, again, all of these are examples of the octet rule, of the central atom having 8 electrons, which is generally observed for carbon and nitrogen and oxygen. There are exceptions that we'll go over this week, but that's sort of the main theme. The 8 electrons is important because it's so common, and our explanation for it has to do with the quantum mechanics. By having 8 electrons around the central atom, they're essentially filling out that quantum molecular shell. Remember, that's a shell. So that shell is now getting filled out by having those 8 electrons. So it's pretty common. Okay, let's talk about double bonds and triple bonds. These are interesting. So these are observed, and they're observed in things like oxygen and nitrogen, and in other types of molecules like HCN. Okay, so these are different. These are not hydrogen, you know, the first 2 don't have hydrogen like the ones we just looked at, but these are diatomics, right? These first 2 are what we call diatomic elements. And that's almost all of our atmosphere, right? The atmosphere on the Earth is oxygen, nitrogen. It's 21% oxygen, it's 78% nitrogen, 99%, just those 2 elements in those forms. Of course, we breathe in oxygen in order to have our metabolism going. Nitrogen is a relatively inert molecule, but that's the atmosphere. So let's take a look at those 2. Here, we don't have to worry about a central atom again, because if you only have 2 atoms, there is no central atom. The center of the molecule is actually in the bond. The bond is actually the center, not the atom itself. So how many valence electrons does each one have? Well, this is in column 6A. So you've got 2 times 6, 12 valence electrons. So now notice how we don't have 8 anymore, we have 12. But again, we want each atom to have 8. So how can that happen? How can each one have 8 if you have 12, right? So here's what you do. You say, okay, we've got 1 bond, so that's 2. So 12 minus 2. So we got 10 electrons left. So here's what I'm going to do. I'm going to write them as pairs around each atom until I run out of electrons. So again, think of pairs. Electrons tend to form spin up, spin down in these orbitals. So that's 2. So there's 6, but I got to stop at 10. So I'm going to go 8, 10. So now we've done all 12 electrons, right? The first 2 were this, the bond, and then the other 10 were those lone pairs. So are we done? The oxygen on the left only has 6. So remember, this is how you count it. That's 2, that's 2, and that's 2. So this one only has 6. But the one on the right does have 8, right? Because there's 2, there's 2, there's 2, and again, there's 2. So this one does have 8. So what do? You can't switch them and have the other one have 8 and the first one not have 8. So here's what happens. If one of them has 6 and the other one has 8, if there are lone pairs, the one that has 8, you push that pair, one of the 3 pairs, to form a second bond. It's kind of cool. So let me show you how I'm doing this. Okay, so keep in mind where we're at. This one has 8, this one only has 6. So the one that has 8, I'm going to take a whole pair, 2 of them, and I'm going to push them in between the 2 atoms. Why? When a pair is in between both atoms get to count the electrons. So when those electrons move between the 2 nuclei, the second atom, the one on the right, is not losing them, but it's sharing them. It hasn't lost them. Remember, loss is where they're gone. They're no longer around the atom. That's oxidation. But what those electrons are doing is they're being shared by the 2 nuclei. So both atoms get to count them. That's why covalent bonding is so powerful in nature, is because both atoms get to count the electrons, right? Electrons are very cool. They spread out over both nuclei so that both nuclei are happier, lower in energy. So how do we represent that? You represent it with 2 lines, because when this lone pair becomes a bond, it's now a second bond. So now both atoms have 2 lone pairs. There's a symmetry to this. The symmetry is that both atoms have 2 lone pairs, and each atom has 2 bonds. That's another phenomenon we see in nature, this idea of symmetry, that one side is the same as the other. You think about life on Earth, a large amount of life on Earth is what we call bilaterally symmetric, meaning one side is just the mirror image of the other side. That's very common in nature, and it's common in terms of chemical bonding as well. There's a stability that comes out of that, okay? And so we have what's called a double bond. Again, it's the octet rule for both atoms. Each atom has 8 electrons now, 8 valence electrons, right? So this oxygen gets to count all of those electrons there. That's 8. This atom on the right gets to count all of those electrons over there. That's 8. 4 of them are shared, and that's what allows this octet rule to occur, is by the sharing of electrons, okay? The main trick in this is that you draw one bond. You start with a single. Then you draw the lone pairs, and it doesn't matter which one gets 2 lone pairs and which one gets 3. It's your choice. But the one that has more, you push a pair over so that both now have 8 electrons. That's the key. Let's try the nitrogen, N2. Same idea. No central atom because there's only 2. One bond. You start with a single. Lewis structures generally start with singles, and then if you need a double or a triple, you'll do it. So how many electrons? Nitrogen is in group 5A, so it has 5. There's 2 nitrogens, so that's 10. Again, notice we don't have a multiple of 8. We don't have 8 or 16 or 24 or 32. We've got 10. So generally, there's going to have to be some kind of sharing going on to get them up to 8. So we've used 2, so we got 8 left over. Now, you can do this in a couple different ways. What I'm going to do is I'm going to put 3 lone pairs on one of the nitrogens to get it up to 8, and then 1 lone pair on the second nitrogen to get it up to 4. You could also, some people might make the argument, hey, put 2 lone pairs on each one. That's okay. You could do that too. You'll get the same answer no matter what. You just need to make sure you don't put in extra electrons. Like sometimes people will make this mistake. They'll say, oh, I know they got to have 8, so I'll put 3 lone pairs over here and 3 lone pairs over there. But that doesn't work because now you've put in 6, another 6, and 2. You put in 14 electrons. That doesn't work. I mean, it looks nice. You got 8 electrons for each one, but that's no good because you can't create electrons. The atoms only have as many electrons as they have, so they have 10. Each has 5, so that's 10. So you can't have more than 10. So be careful of that. Do a single bond and then distribute the lone pairs. Get one of them up to 8 or both of them up to 6. Either way will work. Now what you do is you say, okay, the one on the left only has 4. It needs 8. So what I'm going to do is I'm going to take this pair here and I'm going to push it over. Now that pair is counted by both atoms. So when you push the pair, the atom that had the lone pair, it doesn't lose them. It still has them, so it still has 8. But the one that didn't have it gets to count them too. You're double counting, okay? So now the one on the left has 6, right? It had 4, give it another 2, now it's up to 6, but it needs 8. So here's what you do. You push a second pair. Instead of just doing 1, you do 2 pair. And so now what do you get? Now you have 3 bonds. Each pair that you push over becomes a bond. So now the one on the left still has a lone pair. The one on the right now only has 1 lone pair, but they both have 8 electrons. Remember, this one now has a total of 8 because you get to count all those. This one over here gets a total of 8 as well. So they both have 8. They're both octet. We are set. And you can do a check. Make sure you didn't accidentally put in too many electrons. We know we started with 10. 2, 4, 6, 8, 10. We got 10 electrons. We're perfect. There you go. Okay? It's kind of cool. So that's called a triple bond. Okay, cool name, triple bond. So single, double, and triple. One more. I'm going to do the HCN real quickly. Now, when you have HCN, you got 3 atoms. So which one goes in the center? Sometimes we don't know. You can't know unless you've really worked with the molecule. But in general, just assume the one in the center is in the center. So if you got 3 elements, put the one that's in the middle. Generally, carbon is in the center. Carbon is a real central type atom. Typically, it's in the center. So HCN. Assume single bonds. Okay? Again, the surrounding atoms don't bond to each other. It's just the central. Count up your electrons. Hydrogen has 1, carbon has 4, nitrogen has 5. That's 10 electrons. See, just like N2, 10 electrons. It's not that uncommon to see 10. We've already used 4 because we have 2 bonds. And now surrounding atoms. Do the surrounding atom up to 8 first. Hydrogen is duet. So you stop at 2. You don't going to put anything on hydrogen, but nitrogen is octet. So 2, 4, 6. So in a way, this is just like N2. The atom on the right has 8. The atom in the center only has 4. So what do? If one has 8 and the other one has less than 8, you push a pair from the one that has 8. So I'm going to take a pair, push it over. Now both atoms get to count that. So instead of carbon just having 4, it now has 6. But again, we want it to have 8. So push another pair. So now if you push 2 pairs, what do we have? It's just like N2. We have a triple bond. So now the carbon has 8 and the nitrogen has 8, and this is a triple bond. Remember, carbon and nitrogen, octet rule. Hydrogen, duet rule. And there we go. This is our Lewis structure. It's a cool looking molecule. This is a molecule that's been observed by measuring light all throughout the universe. It's all over the universe. It's on planets and atmospheres of other planets like Venus, I think, has HCN. I think maybe even Jupiter does. It's all throughout the universe. It is believed that HCN can be a starting molecule to make amino acids. So what people are trying to do is they're trying to look through space, look at atmospheres of other planets, and see if they can find amino acids that might have been formed from HCN. If there's HCN out there, there might be amino acids, just like we have here on Earth. Okay? So I just want to show you that we just did sections 8.1, which is the ionic bonding. Not much we're doing in that, just a little bit. And then we did 8.3, which is the covalent bond. And then we did 8.5, which is Lewis structures. We have more to do with Lewis structures. The main focus of this chapter is Lewis structures, so we'll keep on doing, the other sections with those. We'll do a little bit more complicated ones, but we do have to come back and talk a little bit about electronegativity, which is in 8.4. I like to talk about that separately because it's a little bit different of a topic than we're talking about with the covalent bonding. It's related to covalent bonding, but it's just kind of its own species. Okay, so I'll post this. Practice the Lewis structures if you can. At least take, once you take this exam on chapter 6, start practicing your Lewis structures. And some of the problems are really just about counting bonds and counting electrons and stuff like that. But other ones, you're actually going to draw some of the structures. So you should have fun with that. Okay. Very good. So have a great day. I'll see you tomorrow. Again, reach out if you have any questions. I did a lot of the lab reports yesterday, but I'm still got a couple. So if you're missing one, reach out to me. If you sent it to me and you didn't check on Alex, make sure you got it up there. If you didn't, reach out to me and I'll do a check. I found one person I have to update anyways. Okay. Have a great day, you guys.
Thank you.
Great one.
Bye-bye.
Bye. Thank you.